Alright, let's take a look at a couple of problems from Chapter 2, Lesson 1, and it's over average and instantaneous rate of change, and we're getting into the limit definition of a derivative. So before we start the problems, I want to show you a couple samples here. I just want to point out this in case you didn't pick up on this in class. Of course, that notation is basically the derivative, but we're evaluating it at a specific point called C. And so sometimes this is called a difference quotient, and it's basically just the slope. On the bottom we have delta x, and on the top we have delta y. So it's just the slope, the rise over the run. But notice the definition says as x approaches C. So in other words, we're making the slope of the secant line so close to the value we're looking for that it tends to go to 0. So of course you recall that dividing by 0 is not allowed, so we're going to have to use some factoring techniques to solve these when we evaluate them. But so that with that goal in mind, let's go ahead and take a look at the first problem. It says, what's the instantaneous velocity? So we're looking for the rate of change of an object that's free falling, and they've given us a function defined by s of t. So just so we get comfortable with the notation, this is what we're looking for. S prime at 3. So instead of using c, we're going to use actually a number 3 because that's what they gave us. So to find this derivative, or the instantaneous rate of change, it's a limit as t approaches 3, because we're using t variable in this problem, and f of t would be just the function 400 minus that 4.9 t squared minus, this time we're going to plug in R3 for t, but I don't want to multiply this out just yet. Okay, and it's all over t minus 3. So you can see right now, just looking at the denominator, that this is going to be undefined if we try to directly plug it in right now, so don't even bother. We'll go down and see if we can simplify it. Now the first thing you notice is that you have a 400 here and you have a 400 here. So if you distribute that subtraction sign, those two quantities are going to cancel out. And then you notice that you have a 4.9 here, t squared, and you have another 4.9, which is going to end up being multiplied by 9. So we have a common factor, so we don't want to multiply that 4.9 by this term right here. So let's go ahead and recall also that you're going to distribute that negative to that other negative sign over there, which becomes positive. So we could factor out 4.9, but we also could easily factor out a negative 4.9. So let's do that. We have negative 4.9, and if we factor a negative out, then that t squared becomes positive, and then we have our 3 squared left, 9. So we have t minus 3 on the bottom. Okay, so just to reiterate, if we redistribute that negative 4.9 to both terms inside the parentheses, we are right back to where we started up on the top with this term and this term. Okay. Alright, so let's continue on and recall that this is still the limit as t is approaching that 3-second mark. Alright, well, if you look at the numerator, you got to try to factor that out, and since you have a square minus a square, it's going to be able to factor out. You still have your negative 4.9 there, and we have our t plus 3, and we have a t minus 3, And you should be able to recognize that you got that in the denominator as well, so that of course can cancel out. So those two terms cancel each other out. All the while, this is still just a limit problem, just like last chapter. So with those two items gone out of the numerator and the denominator, we can directly plug in our t equals 3 into what's left, which is everything in the numerator. So no longer are we going to have a divide by 0 problem. So we have negative 4.9 times t plus 3. That's the only quantities left. So if you go ahead and plug in your quantity for 3 into your t, you should be able to come up with the solution for that. Okay, well, let's see if we can take a look at problem number 9 and see what we come up with. If I can find it again. There it is. Alright, so in this problem, they want you to find the derivative of c, f prime of c, when the c value is equal to 5. So we'll just set this one up. I'll let you solve this one, but just want to make sure that we understand the notation. So what they're asking us to find is the derivative evaluated at 5. Whether it's 5 seconds or 5 meters, we're not really sure, but it's not too important. So what's our limit going to be? It's going to be the limit as, in this case, everything's written in terms of x. So it's the limit as x approaches 5 of f of x minus the function where we plug in 5 for every x that we have in the original function. And then on the bottom we have x minus 5. So just remember that this is nothing more than delta y over delta x. And it all comes back to slope. It's rise over run. So regardless of the function, we're just looking at the slope at some exact instant. In this case, it's at 5. So let's just write the top and then I'll let you finish the rest. So it's x squared minus 7x plus 2 minus, plugging in 5, we get 25 minus, oops, that's not 10, that's 14. 7 times 2, or excuse me, 7 times 5, 35. And then we have plus 2. So we were able to, and then we have, still have x minus 5 on the bottom. So we still have that divide by 0 issue going on here. This is still the, so you know, you can do a couple of simplifying before you finish. That 2 is going to cancel out with that positive 2 because of this subtraction right there. So those two items are gone. So you have these two like terms left in the second half of the numerator. So it looks like a negative 10. So you could replace this with a negative 10 and now distribute the negative to that negative 10, and now you just have to take care of this polynomial, x squared minus 7x plus 10 all over x minus 5. So obviously you're going to have to factor this guy out, the numerator, and if we didn't make a mistake, x minus 5 should be one of those terms. Okay, so finish that one up, and hopefully the concept is starting to sink in a little bit. So the average rate of change is just the slope of the secant line, and the instantaneous rate of change is the slope of the derivative. Okay, we'll see you next time.